So, the second lecture on Ganitasarasangraha of Mahavira, the outline is something like this. First I will be discussing this linear indeterminate equation or Vallikara Kuttakara as it is called here, then 2 and more simultaneous indeterminate equations, and there are other kinds of indeterminate equations. Then what is known as Vichitra Kuttakara, truthful and untruthful statements. Then sums of progressions of various types, variable velocity, these broad variable velocity problem, this is broadly the outline of this lecture. So, this is a linear indeterminate equation is of the following form. Suppose you are given is equal to y, by, is it what it is? Sorry, to use for consistency. So, given this one equation in two unknowns x and y, so a and b are integers and you have to find integral solution for this, right. If it is if x is any real number, then it can always be solved and y can be correspondingly will have a certain value, but here it is specified that x and y are integers. So, only certain integers will satisfy this equation. It will not be unique, the solution will not be unique, but there will be a set of solutions for this equation with integral values for x and y. So, that is the linear indeterminate equation. So, it is called Kuttaka in Indian mathematics and astronomy texts. It has been discussed by Aryabhatta himself first in Aryabhatiya, and then Brahmagupta discusses it in his Brahmasputa Siddhanta, and now Mahavira also he has discussed this. So, I will give how Mahavira has handled this and the examples he has given, okay, that is by of interest. So, now Kuttaka was considered so important in Indian mathematical tradition that in fact algebra was called Kuttaka. The chapter on algebra in Brahmagupta's Brahmasputa Siddhanta is called Kuttaka. So, that is the importance that was given to this, and it has various applications. So, first I will discuss how it is solved. As I told you, he is not the first to solve. Aryabhatta and Brahmagupta also have given the way to solve it. What Mahavira, how he has described the solution is Chitva Chedena Rashim Prathama Phalam Apohyam Aptam Anyonya Bhaktam Sthapya Urdvadha Yatodho Matiguna Mayuja Alpe Avashishte Dhanarnam Chitvadaha Soparigno Pariyuta Harabhaga Adhikagrasya Haram Chitva Chedena Sagrantara Phalam Adhigagranvitam Haraghatam. So, divide the given group number, I will read it, and of course, one will understand only when I describe it in the with using the notations. So, divide the given group number by the given divisor, discard the first quotient, then put down one below the other various quotients obtained by the successive division of the various resulting divisions by the various resulting remainders again. Put down below the optionally chosen number, which with the least remainder in the odd position of order in the above mentioned process of successive divisions is to be multiplied, and then put down below this again this product increased or decreased as the case may be by the given known number, and divided by the last divisor in the above mentioned process of successive division. Thus, the Vallika or creeper like chain of figures is obtained, that is why it is called Vallikara Kuttakara. In this, the sum is obtained by adding the lowermost number in the chain to the product obtained by the multiplying the number above it with a number immediately above this upper number. This process of addition being in the same way continued till the whole chain is exhausted, this sum is to be divided by the originally given divisor. The remainder in this last division becomes the multiplier x. This at last is the solution he is describing, with the originally given group number is to be multiplied for the purpose of arriving at the quantity which is to be divided or distributed in the manner indicated in the problem. I mean, whatever is given in the brackets, that is not there in the verse itself, but for completion of the many things would have been implied in these works. So, the translation is including that. So, what is done is the following, it is much easier done than said. So, you are solving this bx plus b is equal to ay. Okay. So, now we are using essentially you use a similar procedure which is similar to what you do for finding the highest common factor between a and b, apavartana. So, bx plus b is equal to ay. So, you do this mutual division or the so called Euclidean algorithm. So, then a b this thing quotient is q1, then the remainder is r1. So, now divide a by this remainder r1, then you get the quotient q2 and the remainder r2. Then again r1 you take here and divide r1 by r2, quotient is q3 and remainder is r3, and so on till you get a small number here. Okay. The important thing is that this Kuttaka linear indeterminate equation is much more than Euclidean algorithm. Something more is involved here. It is stopped there, but much more is required to get the solution of the problem which was posed here. So, here he stopped at the nth remainder r5, which is least. It does not, the verse does not specify. It can be, in fact, you can go on till you get 1. So, in the above case n is equal to 5. Okay. I have put it there like that. Now, discard the first quotient q1. Okay. First quotient q1 discard, the other quotient q2, q3, q4, q5. So, that you write as a Valli, that is a column one below the other, and we should choose a number p such that p r5 plus or minus b is divisible by r4. Here plus is chosen when n is odd and minus is chosen when n is even. The number p is written below the column starting with q2 etc. and ending with q1, and below this the quotient p r5 plus b by r4 is equal to q. Okay. So, you are going on, right. The sequence of coefficients we write it like this, q2, q3 etc. qn. Of course, the first quotient q1 is not considered. So, now after q1 you write the number p such that p multiplied by the last remainder and added to b is divisible by the previous remainder, that is in what we have shown p r5 plus b is divisible by r4, and below that you write the quotient q. So, now in the next step you delete this. So, then we do what we do is we take this into this plus this, qn into p plus q. So, we write it here, below this we write p, and the other things are the same above it. So, in the next step what we do is this is multiplied by this and then this is added. So, that will be the is qnp plus q. So, this is deleted and the upper entities are the same. So, you go on like this till only two quantities remain. So, that you write as T1, T2. Yeah. So, if you give some example, then it will be clear. Okay. It is actually pretty simple. So, we have given in the course we have given this procedure, and almost everybody would be able to solve it. So, you just have to understand the procedure, you just write it down one, then you will know. So, solve the equation 63x plus y is equal to 23y. So, you have to solve this equation for integral x and y, right. So, you do this mutual division, 63 divided by 23, quotient is 2, remainder is 17, then 23 is divided by 17. So 1, 6, 6, 17, 2. So like this 1. In fact, we could have stopped here, but I want this number of the total number of quotients to be odd. Then only you will have to be adding. You don't have to bother about adding and subtracting. You can always you could have stopped here, but I'm just then nothing prevents you from doing this also. So such that the number of total number of quotients is odd. That's why I am doing. Okay. Then the R5 is 1 here. R5 is 1 and R4 is 1. Okay. So then you see, we have to choose a number p such that you had got that 1, 2, 1, 4, right? 1, 2, 1, 4 you had got, because the first quotient 2 that you have to leave, all the other quotients you have to take. 1, 2, 1, 4 you have got. Then we have to choose a number p such that when multiplied by the last remainder 1 and added to 7, it is divisible by the last divisor 1. Okay. So here both the last remainder is 1, the last divisor 1 is also 1, right. So we have to choose such that that is R5 p plus b is divisible by R4. Here both R4 and R5 are equal to 1, b is 7. So we can take p is equal to 1. Okay. So that is what you have written below these quotients. From the list the first is removed, as I told you. So 1, 2, 1, 4, then this p, then quotient, you see, R5 p plus b divided by R4, so that is 8. So that quotient you write. So now this into this plus this 12, this is 1 again, so this is removed. So then next this into this plus this, so 1, 2, 13, 12, this is removed. So now next this into this plus this, so 38, 1, 13, this thing, and then last is 51, this into this plus this, so 51, 38. So you have got 2 entries. So now what you have to do is, this itself actually is a solution, but to get the least solution, you note that 51 is 23, that is you divide 51 by this 23, that is this bx plus b is equal to ay. So you divide by this. So then 2 is the quotient and 5 is the remainder is 5. So that remainder is the lowest value for x which satisfies this equation, x is equal to 5, and y is 63 into 5 plus 7 by 23 is 322 by 23, that is 14. So these are the lowest solutions, and the general solutions are clearly 5 plus 23t and y is equal to 14 plus 63t, where t is an arbitrary integer, because what we are solving is, see, 63 x plus 7 is equal to 23y. Suppose x0 is a solution, x0, y0, then if you take x0 plus for any integral multiple of 23, 23m, and y1 is equal to y0 plus 63m, then clearly that also will satisfy, because the 63 into 23 into m will come here and it will come here, they will cancel, and if this satisfies this equation, this also will satisfy the equation. So you will get in fact you have an infinite number of solutions, because m can go from, in fact if you can have negative numbers also, then it will be really, it will go from minus infinity to plus infinity, various integrals, not all the integers, but this, it will be of this form. Okay. Okay. Yeah. In fact, rationale, so one can, I will just give a brief why does it work like this. So what you are doing is, bx plus b by a. So that is what you have to solve, right? Bx plus b, capital Bx plus b divided by capital A, that is y an integer, that is what you have to get. So which I write as q1x plus p1. Okay. So from this one can see that p1 is b minus a q1x plus b divided by a. So, now b minus aq1 is the first remainder. Okay. When b is divided by capital P is divided by capital A, R1 is the first remainder. So, x is equal to ap1 minus b divided by R1. So, now A is actually again when A is divided by R1, the remainder is R2 and the quotient is Q2. So, A can be written like this. So, x is Q2 P1 plus P2 where P2 is this. So, again from this one can write P1 is equal to R1 P2 plus B by R2. And again R1 when it is divided by R2, the quotient is Q3 and the remainder is R3. So, P1 you can write like this and so on, you see. So, you get these kinds of equations. You can have a closer look later. Now, you have to at some stage you are seeing that you are choosing a number. Let us say suppose we stop at the fifth remainder R5 and we call P4 as P. So, the procedure which was given was that this R5 P4 plus B by R4, that must be an integer, you call it P5. So, it is equal to this. So, here we are choosing P is equal to P4 such that this is divisible by R4. So, you get x is equal to Q2 P1 plus P2, P1 is equal to Q3 P2 etc. like this, where we have chosen P such that this is equal to integer. So, that is how you get this thing. So, you have to analyze it a little bit, but nothing more than linear equation. So, this will give the justification of the procedure. Okay. So, this is it. So, what we have obtained is x is equal to Q2 P1 plus P2 through this only. It has been constructed such that this is automatically integer, bx plus b capital A by A is equal to y is equal to Q1 x plus P1 is an integer. Now, let the remainder of x when divided by A be x0. So, then x is equal to x0 plus TA. So, clearly one can see that x0 is the lowest solution and the general solution is x0 plus TA for x, and similarly y0 whatever you get bx0 plus b by capital A is y0, then y0 plus tb is the general solution for y. Okay. Okay. So, now the one equation is so you get the point, right? I mean, because see some equations you may be able to solve by inspection. Okay. Suppose you want to solve this x minus 5 by 8 is an integer. By inspection one can see that any integer, you see 5 plus 8 will solve this, or 5 plus some integral multiple of 8 will solve this, by inspection one can see. But all the problems, can you solve this? No, by inspection it is not easy. So, that is what is given in the procedure which will work for all integers A and capital A and capital B. So, now the second part of Mahaviras procedure for Kuttaka is for the problem such that find x such that let us say b1x plus small b1 by capital A1 is an integer, b2x plus b2 by A2 is an integer, like b3x plus b3 by A3 is an integer, so on. You see, you can go on like that. So, simultaneously I have to solve this. Okay. So, b1x capital B1x plus small b1 is equal to capital A1 into y1, capital b2x plus b2 is equal to A2 like that. So, how do we solve this? In fact, this also has been discussed by Mahavira. Solve this. First equation we have already given the procedure. Let the lowest value of x be S1, and solve this also. The lowest solution for this is, let us say, is S2. When both of them are to be satisfied, see, because the lowest value of this is S1, the general value is this dA1 plus S1 where d is an integer. Similarly, the general solution of this is Ka2 plus S2 where k is an integer. So, from this when you get S1 minus S2 is equal to Ka2 minus Ga1, that is A1d plus S1 minus S2 by A2 is equal to k. So, now it is the one more Kuttaka. You have to solve for a d, you are finding d and k such that both the equations are satisfied, right. So, you have to solve for d and k such that this integral value such that this equation is satisfied. Okay. indeterminate equation where the values of d and k are unknown. So, we find the lowest possible integral value of d, then dA1 plus S1 is the lowest value of x such that this is an integer. Similarly, this is an integer. Let the least value be T1. Let the next value of x which will satisfy this, let us be T2. Then T2 must be T1 plus Na1, because the first equation, if you take the lowest, then if you multiply multiple of A1, that will be a solution. Similarly, for the second equation, the lowest is T1, the common solution we have got, a multiple of A2 must be a solution, and both the equations have to be satisfied when you have to solve both the equations. So, you get, from these two equations you get A1 by A2 is equal to m by n. So, now let A1 A2 capital A2 let P be the highest common factor, then A1 is equal to MP, A2 is equal to NP. So, we can write it like this. So, T1 plus A1 A2 by P is equal to T2 is this thing. So, that will satisfy both the equations. So, you got the point. T1 is the lowest solution which will satisfy both the equations, and the next value is, see somehow both A1 and A2 are involved, and actually the next integral value is T1 plus A1 A2 by P, that is the next higher value. And if you want to go solve the third equation, so then you have to solve this, this also has to be satisfied, this also has to be an integer. So, the solution of this is V is C3 S3 plus CH3, let us say. Now, the solution of the previous two equations will be like this. We saw that is the lowest is this and the general is this, okay, where r is an integer. So, we have to essentially again we have to solve this Kuttaka Ca3 plus S3 minus T1 by L is equal to R. So, that is what you have to do. But of course, third one three equations Ganitasarasangraha does not give in detail, but the two equations he does discuss in detail in his work, and I have already described what it is. So, only if you work out some problems you will be able to understand. It is fairly simple, but because so much is said, one gets maybe rattled. So, the problem is, in the forest 37 heaps of wood apples were seen by the travelers. After 17 fruits were removed therefrom, the remainder was equally divided among 79 persons so as to leave no remainders. What is the share obtained by each? Okay. So, 37 heaps were there. Okay. So, then 17 were removed from that. Okay. 37 x. So, suppose the number in each heap is x. So, 37 x, 17 were removed from that. So, that could be divided among 79 people, 37 x minus 17 by 79. So, that is an integer. So, this is a Kuttaka equation. Of course, this is negative. See. So, this b could be negative also. So, you have to use this procedure which I said. So, the next also is a Dashtamra Rashim Apahaya cha Sapta Paschat Bhakteshtabhi Punarapi Pravihaya Tasmat Trini Trayodashabhi Uddalite Vishuddha Pantairvane Ganakame Katayaika Rashim. When after seeing a group of mangoes in the forest and removing 7 fruits therefrom, it was divided equally among 8 of the travelers, and when again after removing 3 fruits, that heap was divided equally among 13 of them, it left no remainder in both the cases. O mathematician, tell me the numerical measure of this group. So, when you measure, from that heap, if you remove 7, so then it is divisible by 8 because it is distributed among 8 people. So, x minus 7 by 8 is y1, then x minus 3 by 13 is similarly, when you remove 3 from them, it could be distributed among 13. So, these are the two equations you have to solve. So, one can do that. So, as I told you, always Mahavira will have lot of problems for each kind of this thing, a topic that he discusses. So, he will give examples, many also, many equations also involving many more equations. For instance, 3 equations involving 3 linear indeterminate equations. He has given this following problem. Dushta jambu phalanam pathikajanai ratayas tatra rashi dau tyagrau to navanam traya iti punarekadashanam vibhaktaha panchagraste yatinam chaturadhikataraha panchate saptakanam kuttakarartha vinme kathaya ganaka sanchintya rashi pramanam. The traveller saw on the way certain equal heaps of jambu fruits. So, 2 heaps were equally divided among 9 ascetics and left 3 fruits. Okay. So, after distributing them, 3 was the remainder. Again 3 heaps were similarly divided among 11 persons and the remainder was 5. 5 again heaps were similarly divided among 7 and there were 4 more fruits left. So, clearly, essentially what you have to do is 2x plus 3 among the 2 heaps, after it was divided among 9, 3 was remainder. 2x plus 3 by 9 is equal to y1, 3x plus 5 by 11 is equal to y2, 5x plus 4 by 7 is equal to y3. So, the 3 indeterminate equations you have to solve, and you can solve it, you just have to look at the procedure a little more in detail, and you will be able to arrive at it. So, this is one kind of linear indeterminate equation, and of course, that is one of the most important, but Mahavira considers several kinds of indeterminate equations which are of interest. So, another of them apart from this Kuttakara is Vallikara Kuttakara is the following problem he considers. For instance, suppose let m1, m2, mn be the numbers of n kinds of gems. There are n persons, each of them has some different kind of gem, some are diamond, some are emerald, things like that, and let x1, x2 be the value of the single gem in each variety. Let each of them give g gems each to others. What is the value of each gem if the wealth of all the persons become equal after the exchange? Okay. So, that is, each of them will have some gems, particular kinds of gems with a particular value. Okay. So, now there will be some exchange program. Okay. So, for instance, the ith person will have mi gems. So, each of the other persons, ni minus 1 persons, he will give g gems of his own variety. Okay. So, similarly he will receive also from each of the others, he will achieve g gems. Okay. So, finally he will have mi minus ni minus 1 g gems of ith kind, his own kind, and g gems of each of the other kinds. So, the net worth of each person is stated to be the same. Okay. So, what you get is his worth, whatever the number the gems he has, the value of that will be clearly he received g gems from each of the others. So, x2g plus x3g plus etc. xng, and his own whatever he has left with his own gems, that is m1 minus n1 minus 1 into g. So, this, and the other person also similarly will have this kinds of the value of the gems will be like this. So, you will have x1 into m1 minus ng is equal to x2 is equal to m2 minus ng is equal to so on. So, the general integral solution will be x1 is equal to capital M by m1 minus, obviously this x1, x2 etc. they are all inversely proportional to these things. So, you choose m and divided by mi minus ng, that will be xi. So, in fact, Mahavira chooses m is equal to this m1 minus ng into this kind of a thing. So, that x1 is m1 minus ng etc. mn minus ng, in which this is excluded. Okay. In fact, you can take a multiple of that also, multiply all of them, you see, by some number, that also will be a solution. Okay. Because what is said is that the wealth of each person will be the same. Okay. So, that may be any value. So, there is some arbitrariness in this, but the the ratios are what we can actually determine from this. So, he has given the example Pratamasya Chakranilaha Shodashadasha Barakata Dvitiyasya Vajra Srutiya Purushasyaštau Dvau Tatra Datvaiva Teshvaikaikonyaabhyam Samaganatam Yanti Te Trayaha Purushaha Tat Chakranila Marakata Vajranam Kimvida Ardaha. Okay. So, the first man has the 16 azure blue gems, Chakranila. Okay. The second has Marakatam, 10 emeralds. Okay. The third has 8 diamonds. Each among them gives to each of the others 2 gems of the kind owned by himself, and then all the 3 men come to be possessed of equal wealth. So, what are the values of this? So, you can find that. So, here 1 is azure blue, 2 is emerald, 3 is diamond. So, the number of persons is n is equal to 3, and M1 earlier the first person had 16, second has 10, third has 8. So, G is equal to 2 here, the exchange, each of them is giving 2 of his own kind to the others, G is equal to 2. So, Ng is equal to 6. So, you can find this M1 minus Ng in the way he has described the solution. M1 minus Ng is equal to, you can find these things. So, then x1 is this into this, so that is 8, x2 is this into this, so that is 20, and x3 is this into this. So, his algorithm is given here, you see, for solving this. So, similarly consider what is the Suvarna Kutti Kara, because these are, see, all these things. Now, you see, everybody, Bhaskara will talk about it, Narayana Pandita will talk about this, these all, but they will make it slightly more and more slightly difficult problems in that category, kind of a thing. So, that is how Indian mathematics moves. Similarly, Suvarna Kutti Kara, so you have gold of various purities, you can say what we now call it, 24 carat, 22 carat, like that. So, that the measure of purity is called Varna. So, if weights Wi of Varna Vi are mixed, and if there is no loss in weight, so then total weight of the mixture is this, and suppose the Varna of the mixture is this. Okay. So, various Varnas are mixed. So, what is the Varna of the mixture? So, clearly, so that will be the total amount of the pure gold will be same in both if there is no loss. So, then this is the equation. So, Varna of the mixture will be this. And of course, they will also consider some problems where some amount will be lost and all that, the weight may not be the sum of the earlier weights. So, that will be slightly different. And then there are some interesting problem, Vichitra Kutti Kara, truthful and untruthful statement, that also is various people after Mahavira onward they talk about that. So, there are n men, a lady likes m of them. To each of them she makes a statement, I like you only, but that statement is considered as n statements. I mean, she is making one statement, but implicitly it is assumed that she is making n minus 1 statements, I don't like that person, I don't like. So, each of them she is making this. Suppose if she actually likes m of them, then how many truthful statements she has made and how many untruthful statements. So, total number of statements is n squared, because each of them she is making n statements, I like you, I don't like this. Of course, she might not say it, but it is implicit. Similarly, second person also she will say I like you and this thing. And what actually she likes by m of them. Okay. So, then how to solve this? So, here he has given the solution, Purushaha Saikeshta Guna Jiguneshtona Bhavanti Asatyani Purushakrutisthiruna Satyani Bhavanti Vachanani. The number of men multiplied by the number of those liked among them has increased by 1 and then diminished by twice the number of men liked gives rise to the number of untruthful statements. This subtracted from the square of the total number of men becomes the number of statements that are truthful. Okay. So, total number of statements is n squared, of them m are liked. See, so m, suppose you consider the subset of m people whom the lady actually likes. When each of the m number of persons is told you alone are liked, the number of untruthful untruthful statements in each case is m minus 1, okay. Because she says I like you, which is true, then I don't like this, m minus 1 others, which is not true. But she also saying I don't like those others in the other subset, which is true, okay. So the untruthful statement is m into m minus 1. Similarly, the same statement is made to each of the n minus m persons, the subset of unliked entities. So for them, the untruthful statement to each of them is m plus 1, because to that individual she is saying I like you, but actually she does not like him. So that is one untruthful statement. Then she is saying, I do not like this subset of these others, which is not true, she likes them, so m each of them. So that is untruthful. And then she says, others in this other subset, the disliked entities, she says I do not like them, which is true. So you have to carefully understand. So the total number of untruthful statements to n minus m persons is n minus m into m plus 1. So the total number of untruthful statements is, so finally, so you have to add these things, m into m minus 1 plus this. So untruthful statement asatyani, n into m plus 1 minus 2m. So total number of statements is equal to n squared. So n squared minus, okay. So this is the kind of thing. So I am sure in the present context also maybe we have to devise some algorithms. So many truthful and untruthful statements are made in the public. There must be a way of analyzing it. So she has given a problem. There are 5 men, among them 3 are like, in fact liked by a woman. She says separately to each of them, I like you alone. Then how many of her statements are true ones? So here n is equal to 5, m is equal to 3. So the total number of untruthful statements is 14. The total number of statements is 25 because this thing is there. So total number of truthful statements is 11 and the total number of untruthful is 14. So that is the thing. 14 then, okay. So now comes a very important verse in Mahaviras Ganitasarasangraha. So he now gives the expression for the combination of R out of n objects. If n objects are there, then what is the combination of R out of n objects? Ekadyekottaratah padamurdvardayatah kramotkramashah stapya pratilomagnam pratilomagnena bhajitam saram. So beginning with 1 and increasing by 1, let the numbers going up to the given number of things be written down in regular order and in the inverse order respectively in the upper and lower horizontal row. If the product of 1, 2, 3 more etc. of the numbers in the upper row taken from right to left be divided by the corresponding product of 1, 2, 3 etc. in the lower order also taken from right to left, the quantity required in each case is the result, okay. So essentially he is, of course he is taking 1 to n, so he is leaving out, starting from n, but it is equivalent to this. Upper row is n into n minus 1 into this, divided by 1 into 2 into r. So factorial n by factorial n minus 1 into factorial r. So this is the, what is given is this essentially. You take the upper row like this and lower row this. See, already combinatorics, this combination were discussed by Professor Srinivas in this context of Chandras and Matrivrutas and so on. See, but here it was not the solution was not given in this form, okay. So it is in a different form. So in the this particular form, it is given for the first time perhaps here. So there is a very, but strangely he does not discuss too many problems and exercises related to that. He only gives them 3 problems. One of the problems he gives is examine the 6 tastes. So 6. So then by mixing them, then how many this thing you will get, a taste kind of a thing. So that is, as you know, that is the total is 2 to the power of 6 minus 1. Then he talks about, so there are some flowers, okay, Ashoka, Champaka, Nilotpala and Ketaki, okay, 4 kinds of flowers. So how many kinds of garlands you can make, So, that is a simple thing. So, let us say some 2, 3 only he will discuss, but it is a he really laid the foundation for this combinatorics in a of course, apart from what was actually done earlier in Chandra's Shastra books, and later of course Bhaskaracharya too carries forward this to quite a bit, and then Narayana Pandita carries forward to a very great extent this combinatorics. So, that will be discussed later. So, this is an important thing which is there in the text. So, then he is as I told you that various kinds of linear indeterminate equations are there, and Kuttakas was one of them, and some other things also we discussed. So, there is one more interesting problem which he discusses. Suppose there are n merchants each having some money already, they find a purse. The ith person says, if I procure a fraction ai of the amount in the purse, the net amount with me would be m times the sum of the amount that other merchants have. What is the amount that each of the merchant has, and what is the amount in the purse? So essentially, so that is called Pottalakam, the purse. So, he has given the this thing solution here. So, I will skip this as there is not too much time. So, essentially the problem is the following, you see. So, that is, suppose some amount of money is found, capital P. So, the first person says that I have got this amount x1, suppose I get a fraction a1 of this purse amount, okay. So, then my total amount will be m times the whatever money that others have just now. So, this is this, similarly PA2 plus x2 is this, etc. So, n equations in n plus 1 unknown quantities. So, the solution will be given like this, the solution is given in this form, x is equal to m into b1 plus b etc. minus this kind of a thing. So, and the purse is this, you can check this, it is a matter of small details only, but you should realize that it is an indeterminate equation, because essentially see these are the equations, right, these are there are n equations in n plus 1 unknowns, x1, x2 etc. xn, they are the unknowns, and the amount of money in the purse p, that is also unknown. So, the n equations for n plus 1 quantities. So, and you can quickly see that if the solution is suppose one solution is x1, x2, xn and p, then another solution if you multiply this by any quantity, any number, that also will be a solution, because if you multiply this equation, you see, suppose instead of p you put alpha p, instead of x1 you put alpha x1, if you instead of x2 you put alpha x2, then the same will be satisfied, right. You are just multiplying all the equations by alpha on both left hand side and right side. So, the actually the solution is up to some arbitrary constant, you can say that. Yeah. The ratios are given. So, that is what is interesting. In fact, once if you try to solve these problems to get some integral solutions, then you will know he is a very nicely he has chosen. So, he has stated this. So, I have given some these things also, some example also. 5 merchants saw a purse of money, they said one after the another that by obtaining 1 by 6, 1 by 7, 1 by 9, 1 by 8 and 1 by 10 respectively of the contents of the purse, they would each become with what he had on hand 3 times as wealthy as all the remaining others with what they had on hand together. O mathematician, tell me quickly what money they had on hand and what the value of the money in the purse was. So, here this thing is, the fractions are this, and you can take the LCM will be this. So, the solution will be given here, and the total number, the purse is this is the amount. Okay. So, then he talks about some other problems, problem of arrows. Okay, I will skip this. Yeah, arithmetic progression, as I told you, again some advances are made, a little more complicated things are done. You see this is the arithmetic progression, already it has been hammered that this is the sum by Aryabhatta, Brahmagupta, etc. So, this is the solution. So, now you take the sums of the squares, each number is a arithmetic progression, you take the sums of the terms in an arithmetic progression. So, then he gives this as the result. You can see that one has to use these things, sum of the first 10 integers, sum of the squares of the first 10 integers, then you get the result. And cube also he will, this already was done by Aryabhatta, Brahmagupta, a cube plus a plus b whole cubed, etc. So, then that is you take arithmetic series. So, then take the cube of each of them, the sum of that will be equal to this. We can check that. I think you should try this as an exercise. Then he also now goes to a arithmetic progression in which each term is again a sum of an arithmetic series. Okay. So, the series is 1 plus etc. up to a, and next term is 1 plus etc. up to b, and the last term is 1 plus etc. n minus 1 b, a plus n minus 1 b. So, this is the thing. So, each term of the sum of series, each term is sum of a series in arithmetic progression. The sum can be, in fact, this is also a good exercise. From whatever you do not need anything except what has been done earlier, on this, sum and sum of sums and all that. So, whatever result you had got earlier, that you will use. 1 plus etc. up to a, and then this will go up to a plus b. So, there are many more terms here. In the second this thing term, yeah, suppose a is 20, b is 30. So, the 10 more terms are there in the second this thing, each is a sum actually, each term is in the series is a sum by itself. Yeah. So, similarly this sum of sums and all that, some combinations he has given. Then he has given some more problems, various things, suppose you had a, ar, etc. So, then suppose you have a series, geometric, some series like this, a first term is a, second term is ar plus or minus m. So, it is not just, it is neither geometric nor arithmetic. So, it is you are multiplying by some quantity and then adding or subtracting something. Then this into r plus or minus m. So, those kinds of things are also considered, and one can see that it will be, one can you can find the sum. Okay, you just have to see these slides at some leisure, then you will get this. And then lastly, I will discuss the variable velocity problem, somewhat related to a physics kind of problem. So, the rule for arriving at the common limits of time when one who is moving with successive velocities representable as the terms in the arithmetic progression. So, that is velocity is increasing by a fixed amount after each unit of time. So, that is some kind of a constant acceleration, and another moving with a constant velocity. So, it is Drivagati Radhi Vihinas Chedala Bhaktas Surupakaha Kalaha. The unchanging velocity is diminished by the first term of the velocity in series in arithmetical progression, and is then divided by half of the common difference. On adding 1 to the resulting quantity, the required time this thing is arrived at. So, what is the problem? The problem is the following. You see these are two persons. One is moving with a constant velocity v, constant speed. The second is accelerating. So, when he goes from here to here, the velocity is u, then here u plus a, okay, then here u plus 2a, etc. So, he acquires some more velocity at each step. So, that is called acceleration or constant acceleration, right. So, then clearly what is the time, average velocity must be the same. You see, if they have to meet, the average velocity when they meet must be the same. You see, they should have travelled the same distance. Okay. So, time is the same. So, the average velocity should have been the same. So, then the average velocity is the first person is u plus u, this is arithmetic series, the u plus a into t minus 1 by 2. The second person of course is the constant velocity, average is his own constant velocity. So, v. So, t is v minus u divided by a by 2 plus 1. So, that is what he is saying. So, incidentally distance travelled by each is V into T, you see. So, V into T, and this is equal to ut plus half A into T minus 1, the distance, I am sure it reminds you of this formula, constant acceleration, a body is constant acceleration. In school what you learn is that the distance travel is ut plus half a discrete, that is essentially given here. Of course, he is discretely accelerating at discrete steps. So, that is why you have T into, you will not get the exact thing, T into T minus 1 you are getting, but in the limit when T is large, okay, and such that this product is finite, so then you will get actually that formula. So, this is the kind of a problem that and what is interesting is this is the algorithm which is given, you see, this is the formula is there, okay, and it is given in. So, that is the constant question everybody asks, how did they or did they write equations, in the shloka itself will give Trivagati Radhi Vihina Chayadala Bhakta Sarupakaha Kalaha. Sarupakaha is add 1 kind of a thing, okay, add 1. So, then you take the difference between them and divide by this Chaya is the difference in the arithmetic series. So, divide by the difference by 2, then that is the time. So, that is how they express it. So, then he also considers 2 accelerating travelers and all that, and he considers negative acceleration also, positive, negative, one can be positive, one can be negative, because he is somewhat comfortable with positive and negative things, right, having formulated it in the beginning. So, he ought to be comfortable. So, he gives some problems related to negative acceleration also. Finally, he will give some, not finally, I am saying another important thing, n syllables, how many lagu, guru and all that, what is the total number of mace. This has been discussed so many times, I do not have to say that. So, the answer is 2 to the power of n, and the way to compute 2 to the power of n, that also has been hammered. So, that is also put here. So, I think I will stop here. So, these are the kinds of things that he has discussed. So, he has discussed so many things, but some things I am just projecting for whatever is most important. So, some more things I will discuss in the last lecture on Mahavira. The references are given here.
Seems to be the first one leading with mathematical logic. Aryabhatta and other earlier people, they also discuss something like that, the true and false statements and that.
Yeah, that true, that Vichitra Kuttakara he calls it, true and false statements. Yeah, he seems to be the first person. Yeah. This particular kind of problem, yes, is the first one. So later everybody discusses this kind of a thing. Yeah, yes.
Earlier it is not.
He does not. No, earlier I don't think.
I wanted to say that the gemstone problem,
Yeah.
it looks to me it's a rearrangement problem.
Yeah, rearrangement problem.
It's a rearrangement problem because it's a closed universe.
Yeah.
In which the total value remains the same.
Yeah.
But it's a very complex. It's like a Rubik's cube, etc. There's an analogy in a Rubik's cube, because over there you're trying to get all the colors lined up and so on. So if you think of a simplified Rubik's cube, but this one is a very complicated one because each gem has a value. And every gem is distinguishable, and you can see they are distinguished and they cannot be broken down. So you can't equalize by breaking them down because they're bunches of value. So I just thought it's a fantastic.
Yeah, but of course he has a simple problem of after distributing, what is the value? You see, that's the thing. Yeah. He'll stop there. You can go, proceed with that, or to consider more complex problems, related to this. Yes.
One more thing I wanted to ask. So that indeterminate multiple equations which you had somewhere along the way. Yeah. That is that something that lends itself to a matrix type solution, matrices and determinants?
I don't know. Of course, maybe now it can be formulated now. Of course, they didn't talk of matrix.
Yeah, now if it is reformulated, that's it.
I don't know. I'm not talking about that.
In simultaneous
First problem.
Simultaneously, you are talking about this kind of a thing, right? B1x plus E is equal to, huh?
The Peirce problem.
Oh, Peirce problem. Peirce problem. Yes, possibly, yeah. Possibly. Your Peirce problem is, complexified by Narayana Pandita even more, Yeah. But not matrix, but maybe, it can be. Yeah. Thank you.